Hello everybody. Had special request for a shorter video on energy aspects of climate change. I think Voltaire summed it up pretty well 300 years ago. Humans argue, nature acts. So I want to look at these energy calculations. They involve really big numbers. For a really big number, we need a special energy ruler. So our energy ruler is going to be an atomic bomb, the Hiroshima atomic bomb. We're going to look at energy and carbon dioxide release in 1 year of fossil fuel burning, energy and carbon dioxide release in the fires of Australia, and then the energy in increasing the Earth's temperature by 1, 2, or 3 degrees, and then compare that to how much energy it takes to melt all the ice in Greenland, and how long that might take. Now, since we're using energy, not everybody's familiar with the science units of energy. We're all pretty much familiar with calories. Calorie originally was defined to be the amount of heat to heat up 1 gram of water 1 degree Celsius. Later, when we got some science units, that became joules. And so 1 calorie was equal to about 4.2 joules. And so if you don't know what joules are, then think of calories. As maybe that's an everyday thing that you're more familiar with. Now, we have to also look at joules per second. So how fast are the joules being added or lost? And that's called a watt. Sometimes people refer to that as power. Again, if you're not familiar with the science units, then think of calories per hour. Probably for sure you've gone on a walk or done something at the gym and figured out how many calories you were burning per hour. Same idea. And then we have to do one more thing, and that is the watt, which is a joule per second, per square meter. And so, again, if you're not familiar with the science units, think of yourself calories per hour, and then per person. Each person would be a little bit different. And so each situation, when we do per square meter, will be a little bit different too. And so maybe that'll help out. Okay, first our energy ruler will be the Hiroshima atomic bomb. That has about 12,000 tons of TNT. TNT is for trinitrotoluene, a very explosive organic compound. Each ton of TNT has 4.2 gigajoules. Giga is a really big number, 10 to the ninth, which is a billion. So that's 4.2 billion joules. We have to multiply these two numbers together, and when we do, we get something that's almost not comprehensible to most people. We have here millions, then we got billions, and then we got trillions. So this is 50 trillion joules in this Hiroshima atomic bomb. Okay, now the thing about the Hiroshima atomic bomb is that all that energy was released in just a second. It's so powerful, such intensity, it obliterated a 6 square mile area. Of course, everybody in there. So in Hiroshima, 140,000 people were killed and 80,000 in Nagasaki. So it's a tremendous amount of energy, and that's what we're going to use to measure the energy that we see in our world. If we were to look at a proportion of distance, it might be the same as a 2.5 side of a square, 2.5 miles of a square, or a circle with a radius of 1.4 miles. Okay, everything inside there would be obliterated. That's a lot of energy. What we're going to find is nature puts out a lot more energy than that, amazingly. But nature does things, changes climate very, very slowly, usually over centuries, millennia, or even longer, 10,000 years, 100,000 years. So things change slowly. However, once nature makes a change, you're not going to come back real quick. Okay, on a human time scale, it's pretty much irreversible. So we're making some changes way faster than nature usually does. And nature's not going to let us change back very quickly, so we want to make sure about what we're doing. When we look at fossil fuels, there's 3 categories that we typically discuss. There's natural gas. Natural gas is mostly methane. The good thing about methane is it's less carbon. It's 75% carbon. The bad thing is it has carbon, okay, which makes carbon dioxide. And then we're going to look at petroleum, but we're going to approximate petroleum with octane. Octane has 8 carbons in it, and so that means an octane molecule will make 8 carbon dioxides. So we're going to use that as our approximation of fossil fuels. Now, that is 84% carbon, so not as good as methane. But then we're also going to look at coal. Coal is the worst. Okay, we're going to approximate coal with something called benzopyrene, which has 20 carbons for only 12 hydrogens. So if you look at this, it's about 95% carbon. Coals might even be worse than that. Okay, so coal is mostly carbon, and that's bad in itself because it makes a lot more carbon dioxide. But the thing that's really bad is coal comes with heavy metals like mercury. In fact, mercury is spread all over the world because of all the coal that we burn and have burned. There's also things like sulfur in coal. Sulfur becomes sulfur oxides, and then when it rains out of the atmosphere, it becomes acid rain. So this is not good either. Coal is something we would prefer to stay away from. It is just not good. It's not clean. We're going to approximate all of these with octane because we know information about octane that we can use to calculate energies. So all the fossil fuels that we talk about come from octane. Right? Just a brief look at the energy history of humanity, and we'll use the United States as a proxy for that. If you go back to around the time of the Industrial Revolution, you can see there wasn't much combustion. Okay? People were very primitive in their use, but around this time is when they invented that steam engine. And so they needed fuel to burn that steam engine. And at first there weren't too many people, and there weren't too many steam engines. But you can see there's this yellow line. Follow that line out, and you see that's biomass. So way back here, we're talking probably wood. By the time you get out to our time, there's also ethanol. In the United States, we make that from corn. And in Brazil, they make ethanol from sugarcane. Okay, but you can see it's a pretty low amount in terms of the fuels that we're looking at nowadays. Coal came on pretty quick, very practical, easy to use. Dropped a little bit in the United States, went up, and now it's falling off because in the United States we have fracking and natural gas coming on strong. Now, if you look at the rest of the world, China, India, Australia, they don't have such an abundance of petroleum, but they have a lot of coal. So there's still a lot of coal being burned out in the world. And remember, that's the really dirty one. Petroleum, as soon as it came on, was more practical. It rose up to #1, and that's where it still is today, the #1 fossil fuel used. And then in the United States, particularly with fracking, natural gas has come on strong. And a lot of people like substituting that because it's not quite as dirty with carbon dioxide. Now, the problem for all these guys is they're making carbon dioxide. And we need to make less carbon dioxide in our world. We have changed the balance of nature. Nature had a good balance with the plants and the living organisms and stuff going back and forth with the carbon dioxide, but we have just poured out carbon dioxide. Basically, these fossil fuels are like petrified sunlight and petrified energy that's bringing forth all this carbon dioxide. Now, what we need to replace them with are these alternatives down here. You can see nuclear was coming up pretty good, but it leveled off. People are afraid of nuclear for good reasons. It has radioactivity, can possibly be used in terrorism. But there are alternative nuclear designs that could be more practical, and we might be able to use thorium instead of uranium and plutonium. And so there might be some alternatives. We probably are going to need that nuclear. Other renewables would be like solar and wind and geothermal, tidal, things like that. Solar and wind are coming on strong. Probably will pass up coal. Hydroelectric, it's good, but we've kind of maxed out on the rivers. You need big rivers to do that, and we pretty much dammed them all up already. And then we have to also hope that the water doesn't stop flowing for various reasons, drought or whatever. So our big problem, and it's a big problem, is we got all of our energy up here, and we need to move that down here. And we need to take all these alternatives and move them up here. And you can see the amounts that we're talking about are really large. So a really tough problem. So let's take a look at all the fossil fuel combusted last year. We're going to get that from the amount of carbon dioxide that was put out. So it turns out that we generated 40 gigatons of carbon dioxide. Remember, giga is a billion. So 40 billion tons of that carbon dioxide. Now that comes from the fossil fuels, and remember, we're going to approximate our fossil fuels from octane. Now we have a number that we use to compare molecules and amounts, and that's called a mole. So not everybody knows what a mole is, kind of a chemistry term. But everybody knows what a dozen is. If I said a dozen, you'd say 12. If I said a mole, what we need to think of is 6 times 10 to the 23rd, which just really means a big number. The reason this is so big is because molecules are so small, and we need a whole bunch of them to be able to see them and work with them. So just remember, as a mole, the way you count certain numbers of things. Now, if I'm making all this 40 gigatons of carbon dioxide makes 8 times 10 to the 14th moles of carbon dioxide. All right. So I want to know how I get that from the octane. And when you look at the octane, you see there's 8 moles of carbon in 1 mole of octane. And so it's going to be a real easy calculation because I'm just going to take 1/8 of this amount to see how many moles of octane I needed. So I just need 1 times 10 to the 4th. Now the reason we picked octane is because we know that each mole of octane releases 5 million joules when it's burned. So we're going to multiply these two numbers, that's going to come up with a humongous number. So the number's down here, and when you first look at it, it's not like anything you've ever seen before. So if we look here, millions, billions, trillions, quadrillions, quintillions. So he made 500 quintillion joules in 1 year, and that's probably a number you never heard before. Okay, not that I remember hearing it in common speech, but that's a lot of energy. But we burn a lot of fossil fuels, so we need a lot of energy, and that's what we're seeing right here. Now, all that carbon dioxide that we're making, it goes into the air. A lot of it is picked up by plants. Okay, it's like plant food, so that's really good. It takes carbon dioxide out of the air and makes food for us. Some of it stays in the air, and that causes extra heat of our world, and this is not good. We were in balance, and we're getting out of balance with all this extra carbon dioxide coming out. Another place where it's not good is it dissolves in the water of the oceans, and it makes the oceans more acidic. And this is a problem for the animal life that lives in the oceans, but we don't have time really to talk about this here. And the last place I'm talking about would be on land. Sometimes when you have new mountains, like in the Himalayas, there's new rock there that silicates, and the carbon dioxide can switch out the silicates and become carbonates, and so that takes up some carbon dioxide too, and that's good too. Okay. Now, as far as if we compare these two, the amount of energy generated in 1 year to our energy ruler, which is the Hiroshima atomic bomb, what we find out is that there's 10 million Hiroshima atomic bombs per year. That is a mind-boggling number, okay, in terms of energy equivalents. Remember how big that was. That was a lot of energy. Well, it also turns out there's 32 million seconds in a year, so we could calculate how many of those bombs equivalents are coming out per second. We find that one Hiroshima atomic bomb is the energy equivalent is released every 3 seconds for a year. Every 3 seconds. That is an incredible calculation. Okay, a very shocking result, I would say. Okay, now this carbon dioxide comes from a variety of sources where we're burning fossil fuels. I'm not going to go through these. I'll just mention them. The first one is electricity and heat. That's the number one use. That's at like 25% of our fossil fuel burning. We go down the line. The one that surprised me was transportation. Sitting on a freeway, I think there's a lot of cars there. It must be a lot of our fossil fuel, but it's just like 14% of fossil fuels. So that's everything: trains, planes, cars, all that. And then there's other forms here. You can take a look if you want to look at this in more detail. What I want to look at now is the energy and carbon dioxide release in the recent Australian forest fires. These were on the news everywhere in the world, the biggest fires ever in Australia. What I'm looking at is January 13th, 2020. And at that time, there were 14 million acres that had burned. I think there's more now. I recently saw something over 15 million. That's 0.7% of Australia. Right? Now, I had to make an assumption for the vegetation, so I assumed that there were 20 eucalyptus trees per acre. I looked up, I saw there were eucalyptus plantations that had 200 trees per acre, so I figured 20 is a reasonable number there. Now, if we burn all of that, all those trees, all that acreage, we come up with 3 gigatons of carbon dioxide. That is pretty amazing for this humongous fire that we're looking at, because the whole world burning all the fossil fuels was 40 gigatons, and we're getting 3 more gigatons from these fires in Australia. Okay, that's an additional 7% to the total of fossil fuel oxidation in the world. There's other places too. Amazon. Okay, Amazon's been in the news this year too. Amazon's this huge rainforest area, which is full of diversity and full of plants that are absorbing carbon dioxide. So this is just an incredible resource for us. It's about 1.3 billion acres and spread over 9 nations. They say it's the world's largest terrestrial, that means land, carbon dioxide sink. So that's helping us with this global warming problem we got. However, by 2018, about 17% of the Amazon rainforest was already destroyed, intentionally, by fires, by logging. Okay, they burn it so that they can get land to grow soybeans, to raise cattle. Okay, this is a disaster. Okay, the fires in 2019, just this past year, burned over 2 million acres, and again, mostly intentional. Okay, they say that if we lose 25% of the Amazon rainforest, and we're already at 17%, that we'll reach a tipping point. We'll flip it. It'll become, instead of a rainforest, it'll become what they call a degraded savanna, just grassland. that would be a disaster for life on Earth. Okay, but what about California, Indonesia, Siberia, Portugal, Scandinavia? All these places have had record fires in recent years. California in 2018 burned almost 2 million acres. Okay, so incredibly intense fires. These are records that we're seeing, records broken. Some places they didn't even have really big fires. Okay, let's take a look now at how much energy it takes to warm the entire world by 1 degree. Okay, so I really have to emphasize entire world, because people all the time say the temperature goes up and down 20 degrees, plus 20 degrees, minus 20 degrees. How can that 1 degree be a big deal? But when they say that, just one little part of the world is going up or going down that temperature. We're talking the entire world, everything you see in the entire world, 1 degree. So let's calculate that energy and we'll see it's not a trivial amount. Okay, our energy, of course, comes from the sun. And the sun at the surface is 5,800 degrees, all right? So we could calculate the watts per square meter from that using something called the Stefan-Boltzmann law. And so it comes out 64 million watts. Remember, that's like a joule per second. So if you don't know, think of calories per hour. And then per square meter. A square meter is only 3 foot square, okay? And we're getting 64 million watts out of that. And instead of a square meter, if you're thinking calories per hour, think of per individual. You, your friend, your brother, your sister, and so forth. Okay, that's a lot of energy. Now, as the energy goes out from the sun, it gets more and more dilute because it's spread out over a wider area. By the time it gets to the Earth, it's just a little under 1,400 watts per square meter. But all that energy isn't going to cover the Earth because half of the Earth is pointing away, so we're going to cut it in half right away. And then part of the energy is just glancing at the poles, and so we're going to cut it in half again. And that gives us about 342 watts per square meter. But the Earth has a lot of white parts, the clouds, the poles, North Pole, South Pole, all that snow. And so the light that hits there is bounced back, it's reflected away. And so the net amount that we actually get into the atmosphere and to the surface of the Earth is about 240 watts per square meter. Okay, remember, a watt is a joule per second. So now we want to convert that into a temperature. We want to see what kind of temperature is that going to give us. This is by the Stefan-Boltzmann law. And so if we know the temperature, we can calculate the energy. And if we know that the energy, we can calculate the temperature. It's a very easy equation that you see over here. Energy, constant, very small number, constant, and temperature. So in this case, we know the energy. We're going to solve for the temperature, take the fourth root, and we get a temperature of 255 Kelvin. Now, none of us really think in Kelvin. This is like a science unit that people work with for equations, but if we were the rest of the world, we could use Celsius. So the temperature would be minus 18 degrees Celsius. That's pretty doggone cold, no matter who you are. But in America, we use Fahrenheit, so we'd have to say 0 degrees Fahrenheit. Now, water freezes at 32 degrees Fahrenheit, and we're at 0 degrees. So you can see this is really cold. Our world is not like this. If this was true, we would be the biggest ice cube ever, and we're not. So what is our temperature really? Our temperature is really 288 degrees Kelvin. So for our world in the United States, this would be 59 degrees Fahrenheit. Okay, or the rest of the world, 15 degrees Celsius. So this is a more comfortable temperature. Remember, this is an average. So there's temperatures above, there's temperatures below. This is the average with the greenhouse effect. So then what is the greenhouse effect? So I have a little analogy over here. Maybe it'll work. I hope so. Say we put water in a pot, and then we put a flame underneath it. And so that flame heats up the bottom of the pot. Well, there's water right at the surface there. And so that water picks up that heat by conduction, transferred from the pot to the water. And then the water gets excited and goes up into solutions, moves away faster and swirls around in solution. And up here it can transfer its energy to other water molecules. And that transfer can go up and down, left and right, front and back. It can go in all directions. So some of it will actually be reflected back down, and some of it will be bounced up to the top. But when the water leaves here, new water will come in underneath, and then we have the flames still heating up the bottom of the pot, and they get heated up, and they swirl up into the solution. And then sooner or later, we get this whole thing boiling, and water is escaping at the top through evaporation, but we're constantly supplying more energy to bring more water up to the top. And so we reach sort of an equilibrium here while the water is boiling at that constant temperature. All that swirling around is called convection. Right at the surface, it's called conduction. Now, as far as the Earth goes, we get our energy from the sun, visible light mainly coming in. And so that visible light is kind of like the flame here. And we turn that on every day. Every day when the Earth faces the sun, the surface of that Earth is going to get heated up by that energy. Now, the Earth will pick up that, absorb that visible light, but it will radiate it as infrared, as heat. So we feel the heat coming off. Certain molecules in our atmosphere are really good at picking up infrared. Molecules that have more than 3 atoms, or more than 2 atoms. So carbon dioxide has 3, water has 3, methane has 5. And so these molecules are real good at picking up that energy, and so they get energetically bounced up into the atmosphere, and again they transfer the energy front and back, left and right, up and down. So part of the energy is going to move out as it moves towards the outer space. That energy will escape, but part of the energy is reflected back down to the Earth, and that's going to re-excite these guys over and over. And of course, when these guys get excited away from the surface, new molecules come in, they get excited, and you get this whole swirling of all these different guys transferring their energy around. Okay, so at the surface we call it conduction. Up here we're going to call it convection. Now, the more of these gases you have in the atmosphere, the more you can do this. And so then the warmer the Earth will get before it reaches this equilibrium where it starts transferring the excess energy out to space. Now, we know the total. We want to know the total energy. What we know is the temperature. So we're going to come down here, put the temperature in, and calculate the total energy. So at the temperature that we're at, 288, that's 392 watts per square meter. So remember, joule per second, that would be like calories per hour, per square meter. So we're talking about the Earth square meter. That's about a 3-foot square on a side. Okay, now this is much higher than the amount the sun's pumping into the atmosphere because of this greenhouse effect that we're talking about here. Now what we're going to do is we're going to imagine heating that temperature up 1 degree. So now we're at 289. We can go through the same calculation and calculate a new energy that's coming out. That's 398 watts per square meter. So we compare these two. They look pretty close. It's only 6 watts per square meter different. But then we got to think, how many square meters are there on Earth? Well, if you calculate it out, there's a lot of square meters on Earth. So again, a big number. Millions, billions, trillions. 520 trillion square meters. We have to multiply that by every one of those 392 joules per square meter. But we're also doing it for a year, so we need to bring back our 32 million seconds in a year. So I put that in, and we get a number that is just, it's almost incomprehensible how big it is, 6.52 times 10 to the 24 joules. Well, we do the same thing with our 398, because we've added an extra degree here. It's at 289 instead of 288. And so then we get 6.62 times 10 to the 24. We look at those and we say, oh, that's not too different. 6.52, 6.62, that's only 0.1. But what we're forgetting is this times 10 to the 24 joules. So we take one of those 10s and make this a 1. And so what we're really looking at, excuse me, is 1 times 10 to the 23 joules. Another number that is almost incomprehensible. So we have millions, billions, trillions, quadrillions, quintillions, sextillions. So we went past the quintillions. Now we're at sextillions, 100 sextillion joules. And who the heck knows what that means? Okay, just an incredible amount of energy. But now think what caused it. A 1 degree increase in the entire Earth's temperature. So now what we're going to do is we're going to compare that energy to the energy of all the fossil fuels burned in 1 year. Okay, we were thinking that was like off the chart big. That was a quintillion amount. So I divide these out and I get a ratio of 200 to 1. And you look at that, that's a pretty small ratio. I can understand 200. But remember, this 1 was a quintillion amount of 500 quintillion joules per year. So what that means is this is incredible. It's mind-boggling how much that is. So I would suggest compare this to your daily diet. Okay? So your daily diet, we'll say it's 2,000. Maybe it's less, maybe it's more. Let's say it's 2,000. You're going to have to eat 200 times that to equal the ratio of energy that we put in extra here. 200 times that. That would be 400,000 calories. And you're going to have to eat those in a day. That's equivalent to 114 pounds of calories. If you look at that 200, that's like 200 out of 365, maybe 60% of your yearly quota of calories in 1 day. So we're just pouring on the energy every time we increase the temperature of the Earth 1 degree. Well, what I did was I did the calculation for 2 degrees and 3 degrees. Actually, I did it 4, 5, 6, 7, 8, but only here I'm only going to show up to 3 degrees. So here's our ratio of 200 to 1, okay? And there's our energy that we're making with that temperature. If we go up to this 1 degree, there's our 201. If we go up 2 degrees, we would be at a 370 to 1 ratio, remember, of the extra energy from the increase in temperature to all the fossil fuel burned in a year. And if we go up 3 degrees, we're going to be at 580. If you look at 580 to 1, that's the equivalent of you eating over 1,000,000 calories a day. Okay? Might be good for the first 3 or 4 or 5,000 calories, but after that, it's just not going to work. Okay? Over 1,000,000 calories a day, after day, after day. Okay, so how does our energy ruler measure this out? So all the fossil fuels combusted in a year, we said that was 1 Hiroshima bomb every 3 seconds. That was pretty incredible. But now we're looking at 200 times that. That would be the equivalent of 62 Hiroshima atomic bombs per second. 2 degrees would be 116 Hiroshima atomic bombs per second. 181 degrees Hiroshima atomic bombs per second with a 3-degree increase. We don't even know what this means. It's so much energy. We're just pouring it into the world. I'm going to look at one consequence of this, and that's melting ice, causing sea level rise. This is one of the main things we're concerned about, at least initially. Now, it turns out that Greenland has 15% of the Earth's ice, Antarctica has 85%, and there's less than 1% that's in the glaciers of the world, although that's a very important amount because it provides fresh water to so many countries. Okay, so we're going to look at the melting all the ice in Greenland, and that would raise the Earth's sea level by 20 to 24 feet, someplace in there. Okay, now the energy to melt all that ice in Greenland is about 8 times 10 to the 23. Well, that's a big number because we just were looking at 1 times 10 to the 23 for increasing the temperature 1 degree. So we see that they're in the same ballpark. To melt all the ice in Greenland, that energy would be 8 times the amount to increase the Earth's temperature 1 degree. All right. Now, if we did that all in 1 year, okay, so we added it all in, we put all the energy into heating up Greenland, that would take us 8 years to do that. That's remarkably fast when we think how much ice is in Greenland. Okay, the ice sheet covers 660,000 square miles, and it's about 1 to 2 miles thick. So that is such an incredible amount of ice. Again, it's just incomprehensible. But they're saying we could do that if we took all that energy and did it in once to Greenland ice. That's not going to happen, of course. Okay, so what if, since Greenland is about, I calculated out about 1/240th of the Earth. Okay, the area of Greenland is about 1/240th of the area of the Earth. So I said, let's just put 1/240th of the energy into melting Greenland's ice. So if we did that, it would take around 1,900 years. That sounds, sounds like a long time, but geologically, that is super fast. Greenland ice has been around for thousands and thousands of years. To melt it all would require, 10,000, 20,000 or more years. So this would be like world record speed if this happened. But in terms of us, human beings, this is a very, very long time. It would give us a lot of time to adjust. However, we've already heated up the world 1 degree. Okay, we've had enough energy to heat it up 2 degrees. So we're going to see 2 degrees for sure. And the way we're going, we're not stopping, we're not slowing down. So it's very likely we'll heat it up 3 degrees. We hope that it's not more than 3, and that's why I stopped my calculation at 3, because I don't really want to look at 4, 5, 6, although that's a possibility by 2100. So let's come down. Let's just use the 3 degrees, because there's another thing that I did not mention, and that is while we heated up the Earth 1 degree, the Arctic heated up 2 to 3 times more than that. So it makes sense that we could use the 3-degree amount. Now, if we use the 3-degree amount, and we say that 1/240th of the energy goes into Greenland, which is very reasonable since that's the fraction of the Earth's area that it is, then we can take a look. So what I did was I plotted that out. Here's our 672 years that we're looking at. Okay, none of us are going to be around there. But what I did was I just plotted a straight line, so we looked at a linear increase of temperature, and I stopped it at 2100 because that's where everybody does calculations now, but that's not going to happen. I mean, the carbon dioxide is going to stay there for hundreds to thousands of years, and so it's going to keep going up, 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 up. So if I stop it at 2100, that would be about 2.5 feet sea level rise. So that doesn't sound like a lot, but you're talking about a large part of the world is built on the coastal areas of countries. So this would be a horrible thing for every harbor that you have. Every country in the world, the coastal areas would be inundated with water. Bangladesh would be flooded. South Florida would be flooded. The Mekong Delta grows rice for Southeast Asia, would be flooded. And 2100, we're also thinking there's going to be a population around 11 billion people. Okay, so we're going to need more land, not less. We're going to need more food, not less. So this is like a major problem, crisis that we face. If you think back to that slide where I showed the energy use in history, we're using all the fossil fuels, a whole lot, and then all the alternatives are way down at the bottom, hardly any, and we have to switch those guys, flip those guys to get us out of this problem. Okay, so I would just point out, if you're checking your own health, we check our blood pressure, we check our cholesterol, we check our blood sugar as a measure of our health. The ice in Greenland is a measure of the Earth's health, and it's looking precarious. It's looking in danger. Additionally, there's other places that have ice. Antarctica has 85% of the ice. It makes sense that some of that's going to be melting too, and so that could accelerate all these things that I'm talking about here. Also, all around the world, people are pumping water out of the water tables, the historical water tables that have been there for centuries or thousands of years, millennia, and that water is flowing into rivers out to the ocean. That's also increasing the ocean. In addition, as the oceans get warmer, the water expands, so that also increases the sea level. We have a lot of things increasing the sea level, so this is just an example of a possibility. Now, how fast are we increasing the temperature? It turns out we're going fast, really fast. So I put here, they have their temperature record back to 1880. You see it kind of bounces around. Sometimes it's a little higher, sometimes it's a little lower, just natural fluctuations. And we could go back, many, many hundreds of years, and it's going to be in the same ballpark. So I think we could go back around 10, 11, 12,000 years, same ballpark. But you'll see what happens in 1970. We hit this mark, which looks like 1960, but we started up to 1980, and we never went down. Okay, we're up, up, up. We did go down a little bit in the early 90s, and the climate change deniers jumped all over this, and they pointed out how the people saying the temperature's increasing didn't know what they're talking about, because look at it, it's going back down. Well, this turned out to be because of a volcanic explosion, Mount Pinatubo eruption, and it spewed out a lot of sulfur oxides. And the sulfur oxides reflect visible light. And so we weren't getting as much energy into the atmosphere, and you could see the temperature started to drop. But this washes out with water, washes into the ocean and onto the land with rain. And as soon as that's all washed out after a year or two, you can see what happened is the carbon dioxide was still there and the temperature kept going up and up and up. Okay, so if we just look at this last 50 years, it went from this to this, and that is 1 degree increase that we're looking at in 50 years. So I just plotted that out as degrees per year, and that's like 0.02 degrees Celsius per year. Sounds like a small number, but it's incredibly big in terms of historical temperature rise. Also, if you look over here at the temperatures, okay, these are the annual high temperatures, average temperatures. The last 6 years are the warmest 6 years on record. Okay, we're going up and up. 2019 came in second place. 2016 is first place, but they're all fluctuating up here around 1 degree. Okay, so this is not a good sign. Okay, this is what people are saying is going to happen, and it's happening. Now, if we look at carbon dioxide back a long, long time, say 400,000 years, carbon dioxide temperature, look back 400,000 years, temperature bounces up and down, up and down, up and down. Okay, and this is due to mainly something they call the Milankovitch cycles, which has to do with how the Earth is orientated towards the sun. I don't want to go into all, there's like 3 aspects that we could look at, but I'm not going to go into all that detail. But carbon dioxide tends to fluctuate with the Milankovitch cycles. So when the temperature goes down, the Earth gets colder, and the ocean gets colder, and more carbon dioxide dissolves in the ocean, so it's pulled out of the atmosphere, which also makes for a smaller greenhouse effect. But when the Earth starts to warm up, such as when we get closer to the sun or face the sun more, it gets warmer, then the carbon dioxide kind of bubbles out of the ocean, kind of like a hot soda pop bottle. If you pop that open on a hot day, it sprays all over the place. But this is just carbon dioxide coming out. And then you have more carbon dioxide in the atmosphere, and that helps with the greenhouse effect too. So it makes the Earth warmer. And so you can see we're bouncing pretty big range here, about -8 I have, and maybe +2 or 3. Okay, that's what we're looking at in terms of the extremes. But we're talking tens of thousands of years that this happens. Okay, and so when we're up here warm, they call it an interglacial warm period. And when we're down here cold, they call it an ice age because a large portion of the world is covered in ice. Now, if I took this last little part right here, and I just made an estimate, so it's going to be a very crude estimate. So I'm saying we're going up about 8 degrees, and it's around 20,000 years. And so that would be 0.004 degrees Celsius per year. If I divide the current increase that I pointed out up here, 0.02, by historical, that would be about 50 times faster in terms of what we're doing right now, in terms of the warming that people are doing. Now, it could be less. Maybe my numbers are off, so maybe it's 20 times. But even if it's 20 times, that's still an incredible increase in temperature for what we're doing compared to what geological time does. Now, you'll notice right here, it kind of flattens out. This is when civilization started developing. Okay, about 12,000 years ago, we came out of an ice age. We hit this warm spot right here. And so we've been doing really good at this temperature right here. And civilization, we could grow food, we could develop cities and culture and religions and everything else. But right here at the very end, and I can't even show it accurately, is this little part right here, this 1 degree increase that we're shooting up. It would have to be really a straight line up. And we've gone up 1. It doesn't look like it's slowing down. So it's possible, and I say it's going to happen, we're going to go up 2, and probably 3, maybe 4. We don't want to do that. But worst case scenario, we would go up about 6 degrees in about 100 years, which is basically instantaneous on geological time. Okay, so what we want to do is kind of stop this. We're going to hit 2. Maybe we could stop it there. Okay, a lot of this comes from carbon dioxide, so I'm also looking at the carbon dioxide record. Right here is the Industrial Revolution. Remember, we weren't burning anything then. Maybe a few fires here and there, but it wasn't changing anything. We could go back about 12,000 years, and the carbon dioxide's pretty flat. It's around 280 parts per million. Okay, but right here is where we started burning. But at first, there weren't too many steam engines, and there wasn't too many people, and they weren't burning too much fossil fuels. So there was a slow rise in temperature. Now, how do we know these carbon dioxide levels? Well, what they've done is they bored down into Greenland ice and Antarctica ice, and they figured out the carbon dioxide that was in the Earth at these particular times. Okay, so we're going up and up, kind of slow. You'll notice in 1958, they actually set up an experimental research station in Mauna Loa, Hawaii, way up the top of a mountain, so that they got the actual carbon dioxide levels in the Earth. So from 1958 on, we're measuring this experimentally every single day. And so what you see is that it's not slowing down. Okay, well, we got more people. We got more cars. We got more factories. We got more everything that's burning fossil fuels, and it's just shooting up, up, up. If we looked at 1960, it was increasing about 0.8 parts per million. So that's pretty big historically, but that's not anything like we're doing now. 2019, we're going up about 3 parts per million, and probably, the way it's looking, more, 4 parts per million or more. But let's just take this 3 parts per million. And what I did was I just multiplied it by 10 to go out by decades here. 2030, 2040, 2050. So at 2050, if we just increased 30 parts per million every decade, we would be at 500 parts per million. Okay, we're currently at 415, and people are alarmed at 415. Okay, people were willing to stop at 350. They even have an organization, 350.org. Okay, but for the longest time we were at 280. Now we're at 415. Remember, this carbon dioxide absorbs heat, and that allows more water to go into the atmosphere, which also absorbs heat even more than the carbon dioxide. So we have this problem of heating up our atmosphere. Now, if we kept going to 2100, we would be well over 600, 650. And that's assuming we're only going up 3 parts per million. Remember, there's going to be more people. Around 2050, there's supposed to be around 9 billion people. Around 2100, there's supposed to be around 11 billion people. They're all going to want to live a higher standard of living. We have to find a substitute for fossil fuels. Okay? So if we look at carbon dioxide back 800,000 years, what we see is that it never really went over this amount. Here's this one little dot right here where it was 300 parts per million in the last 800,000 years. Now it's up and down, up and down. When it's up, warm period. When it's down, we're talking about an ice age. Okay, ice ages are not good either. We need that. But we hit this nice little climate sweet spot in the last 12,000 years where civilization actually developed. And from the Industrial Revolution, you can see what we've done is we've just shot straight up. It's like a geyser coming out at Yosemite. Okay, right now we're at 415. It looks like we're not stopping, but we have to stop. Okay, now can the world, I always hear all the time, the world's had way higher carbon dioxide levels. And that's true. There was times in history where carbon dioxide levels were 6,000 parts per million. But guess what? There weren't any people there. There weren't coastal cities on every single coastline of every single country. Okay, if we go to 6,000, we are done. Okay, we're just trying to keep it down, under 400 at this point. So we have a real problem. We have to act on it. Now, every 6 years they come out with this report. They look at all these scientists and all these research people look from countries all over the world, and they look for ways that, what is the health history of the Earth, and then what are things that we could do to reduce carbon dioxide. So they have suggestions in there, like increasing use of electricity, decreasing use of fossil fuels, so that electricity we're using more, coal we dropped to 5%, oil we dropped to 13%. That's a good idea, but we're not doing it. Okay, increase nuclear and so forth. We have these possibilities, and we need to research them, implement them, and we need to do much, much more. Okay, now this report was 2014, so there should be one coming out in 2020, I'm thinking, because they generally come out every 6 years. And this will give us a more current report on our status, what we've done, what we need to do, and so forth. This is fully online. You can read the whole thing. When the other one comes out, you can read the whole thing and take a look at that. Now, in the middle, they had a special report. They called it a special report on global warming. They were saying, how can we keep the temperature to 1.5 degrees Celsius by 2100? So this was their plan, and you can see how this plan sounds to you. Okay, they want to take human-caused emission of carbon dioxide, and they want to go back to 2010, and then they want to cut that to 45%. Okay, now they give us 10 years to do that. This has to be done by 2030. So we have to basically go back to 10 years ago, cut it to more than half, and do that by 2030. That sounds pretty hard with everything increasing along the way. And that's only the first thing. And we have to reduce it to 0 by 2050. Okay, so you can see this looks pretty ridiculous. And that's supposed to keep us at 1.5 degrees as the maximum temperature increase. So that's why I keep saying we're going to see 2 degrees and probably 3 degrees. So if that happens, then the consequences are more severe. It's not the end of the world, but it's going to be the end of a lot of situations around the world in terms of fossil fuel, in terms of coastal sea areas and stuff like that, and growing food. I'll leave you with a couple of quotes. Okay, we are the first generation to feel the impact of climate change. We are the last generation that can do something about it. Okay, it's happening right now. And this is one that's more personal to each of us. You cannot go through a single day without having an impact on the world around you. What you do makes a difference, and you have to decide what kind of difference you want to make. And I hope all of us can make that difference. Thank you for listening.